This is the Stats Sensei, and I'm here to do some test corrections with you for the Unit 4A test, multiple choice test for means. Please note that when you're going through the process, you not only need to write down the problem number, the letter associated with the answer, but anything that I have written down, you also need to include as well. It's going to be really important to your understanding and helping you with that AP exam that's coming up. So the process of producing pain reliever tablets yields tablets with varying amounts of the active ingredient. It is claimed that the average amount of ingredient per tablet is at least 200 milligrams. I'm going to go ahead and highlight that because we're going to come back to that and need to talk about that in a moment. So that's our claim. The Consumer Watchdog Bureau tests a random sample of 70. That's also important. The mean content of the active ingredient for this sample is 194.3 with a standard deviation 21. What is the approximate p-value for the appropriate test? So first off, when I say the word approximate, they're saying, hey, choose the best answer. What's closest to this? So we need to take a look at this and see what we actually have. They're saying that it's at least 200. So the claim is mu is equal to 200. And actually they're saying it's at least 200, so it could be more than 200. That means the alternative, the watchdog group, is concerned. What are they concerned with? They're concerned whether or not it's less than 200. If it's more than 200, they're happy because the claim is that it's at least 200. So if we're drawing a picture of this, which you need to do as well, we have a 200. We have a sample mean, an X bar of 194.3, and we're looking for that area. So we're looking for the probability that T is less than 194.3 minus 200 divided by our sample standard deviation was 21 divided by the square root of 70. So, and the reason I know it's a t-test is because we are working with the standard deviation from the sample. As soon as it's standard deviation from the sample, it's a t-test. So we're going to go to the calculator real quickly and run this as a, go to stat test. This will just be a t-test. My mean, well, they're claiming it's 200, so that's the null hypothesis, but we actually got a sample standard deviation of 194.3. And we had a sample standard deviation of 21, and we had 70 tablets. And then we ended up going to the less than. We ended up with the probability that T is less than negative 2.27. Equals 0.013. So this will be looking for my closest answer, and A happens to be my closest answer. I sure wish it had been closer than that, but that's as close as I give it. And I should tell you this, that every single problem on this test was on an AP exam. So none of this was things that we chose randomly. They were actually from old AP stats exams. Number two, makers of a new pain relieving medication claim that it relieves chronic pain faster than the current. So that's probably important. So I'm going to go highlight that. Pain's faster than the current. That's the claim. A double-blind experiment was conducted in which 10 people who experienced chronic pain, so we have a sample of 10, were randomly selected to take either the new or the current medication. Each of the 10 people recorded the time in minutes from taking the medication until pain relief. After an appropriate time, each of the 10 people took the other medication. Whoa, wait a second. Each of the 10 took one medication and then they took the other. That means they were tested twice. This is important because this lets us know that they were tested twice. So we know we're dealing with a paired t-test. We know that the t-test that what we're working with is a paired test. the medication each person took first, recorded the time from taking the medication until pain relief, was randomly determined. And because both medications looked the same, the people in the study did not know what medication was taken first. The table is shown summary statistics for each of the results. Now, once again, I'm going to say, here's what they said. They basically said they took it twice. All right. They were randomly assigned to take one first. They don't know which one they took first, but they're randomly assigned to take one. And then after a certain amount of time, they took the other. So since it's a paired, we need to work. We're not going to look at the average of one and the average of the other. We're going to look at the difference. And since they said new minus current, we're expecting the new to take less time. So here's what our null hypothesis should be. HO mu D equals 0. And what they're hoping to show is that it took less time because we want new minus current. So writing our formula, T equals X bar D minus mu D SD divided by the square root of N. So we want the probability that T is less than, we ended up with a sample mean of negative 0.425, negative 0.425, because that was the difference, minus population mean is 0, that came from here, came from our null hypothesis, 1.395 divided by the square root of, we had 10 people, and once again, we had 10 people that were tested twice, and that makes it the paired. So SPAT, test, t-test. The mean, our mean was 0. The sample mean that we received was 10. We had a sample standard deviation, excuse me, we had a sample mean, I said that wrong. Our sample mean was negative 0.425. And by the way, I got to tell you something about the calculator. It's really picky about this. So make sure when you're using the negative sign, not the minus, use the negative to get that negative 0.425. So negative 0.425 with a standard deviation of 1.395. And they were saying less time. And we had a sample size 10, so we need less highlighted. So we end up getting a t-statistic of negative 0.96. So we want the probability that t is less than negative 0.9634. And that equals 0.1802. And it was nice of them this time to give us an exact response. Makes us feel a little bit better. So the answer to number 2 is A. All right, number 3, test the hypothesis mu equals 0 versus mu is greater than 0 was conducted using a sample of size 7, all right? The test statistic was 1.935. Which of the following is closest to the p-value? Well, notice they didn't give us the standard deviation or anything like that. So we're gonna have to go to a different spot on the calculator. All right, so what we have is we have a t-statistic, we know the t is centered on 0. So that's the mean of the t distribution. And they gave us a t-statistic of 1.935. So I'm looking for this area. Well, this is kind of nice because there's not a whole lot of work to show. This is going to be a second vars TCDF. So you probably should write this down, TCDF. All right. So second vars, TCDF. And we have a lower bound. Well, the lower part of my shading is at 1.935. And the upper bound is infinity. And our degrees of freedom, we had a sample of size 7. So our degrees of freedom are 7 minus 1. So I'm going to write that down because you need to make sure you know that. Lower TCDF, lower equals 1.935. Upper equal to infinity. and degrees of freedom was 7 minus 1. When we do that, press enter a couple times, we end up getting 0.057, and 0.05057, the closest one to that is D. So number 3 is D, and once again, it's just a simple TCDF. Okay, next question, number 4. A statistics student wants to compare the mean times needed to, and by the way, I'm going to come back to that word because we're going to need that. We're going to compare the mean times needed to access flight information for 2 major airlines. 20 randomly selected, so that's also important. Students access one airline's website and the time required to locate the flight information using the website had a mean of 2.5 and a standard deviation of 0.8. 20 different, we have another group, different selected students access the other airline's website, and the time required to locate the flight information using the website had a mean of 2.1 and a standard deviation of 1.1. Assuming that the conditions for inference are met, which of the following about the p-value obtained from the test and the conclusion is true? All right, so it's like, oh, p-value, I know I'm running a hypothesis test. Gosh, I also know, just reading this, it sounds like it's 2 separate samples. So I have 2 separate groups, test 2 separate airline websites. This is a 2 samples. So then I need to determine what my direction is. All right, what is my null? What is my alternative? And I look and I read this thing and I don't see anything about direction. All I see is the word compare. And the word compare, if I don't have direction and they're asking me to compare something or look for the difference, this is a not equal. So this particular case, we're dealing with a not equal. So our null hypothesis would be mu does not equal, excuse me, not mu, mu1 equals mu2. One side equals the other side. The other one would be the alternative, mu1 does not equal mu2. We decided it was a 2 sample test, so our formula is T equals x bar 1 minus x bar 2 over S1 squared N1 plus S2 squared N2. So I need to start plugging into that. And I go, well, I know I need to know what my T is, and I need to go, and so they tell me my sample mean, I had a mean of 2.5. So this is 2.5. The other one had a mean of 2.1. The next thing, the standard deviation. Well, the standard deviation of the first one was 0.8. And we know that our sample size was 20. And the following one had a standard deviation of 1.1. And it also had the same sample size. So there we go. And by the way, people always say, hey, I know I'm supposed to be putting it 2 times. How would I know? Well, 2.5 is greater than 2.1. If it had been less than, I would use the less than, but since it's a greater than, I'm looking for the probability that, or 2 times the probability that T is greater than, because I know this number is greater than that, so I'm going to have a positive. So I need to run this into the calculator. So here we go. Stat test, and number 4, 2 sample t-test is where we're going. And we're using statistics. You're like, of course we're using statistics. This is a statistics class. Our sample mean for the first one was 2.5 with a standard deviation of 0.8. And our sample size was 20. The next had a sample mean of 2.1 with a standard deviation of 1.1 and a sample size of 20. Make sure you choose the not equal to. And the reason it was not equal, they did not give a direction. They just wanted to compare them. And I end up getting a very large p-value. I get a p-value of 0.197. So 2 times the probability that t is greater than, and our t statistic is 1.315, equals 0.1970. All right, 0.1970. So the p-value is greater than 0.1, therefore there's no significant difference in the mean search times. We know there's a difference. 2.5 is definitely different than 2.1. There is some evidence, but there's not significant evidence to say that there's a difference. So we would say there's no significant difference. So number 4, the answer to number 4 is D. All right. Looking at number 5, to determine whether employees at site X have higher salaries on average than those at site Y of the same company, independent random samples of salaries were obtained for the 2 groups. The data of the summary are summarized below. Okay, so they told us we have 2 independent groups. That makes it easy. As soon as I say they're 2 independent groups, this is 2 sample, because paired is related. So essentially there's a dependency there with a paired. Here we have 2 independent groups. So we need to go ahead and just run a test. Well, since with that being the case, and X being greater than Y. So our null hypothesis is, I'll do this on a separate sheet of paper just like I did the last one. Seems to work. Our null hypothesis is HO mean of 1 equals the mean of 2. The alternative, mean of 1. And they wanted to see if X was greater than Y. All right. And 1 is going to be represent X. This is going to represent Y. My formula, of course, is T equals X bar 1 minus X bar 2, S1 squared divided by N1 plus S2 squared divided by N2. So then I need to plug into my formula. And plugging into my formula, I'm looking at the probability that T is greater than 61,234 minus 60,529 over the square root of 4,352 squared divided by pretty large sample size of 235 plus 3,456 squared divided by 183. So that's pretty well our work shown. And now we need to plug that information into the calculator. So into the calculator, stat test, we're going to drop down to number 4, a 2 sample t-test. And we have a sample mean of 61,234 with a sample standard deviation of 4352 and a sample size of 235. The mean of sample size of a site Y was 60,529 and 3,456 is my sample size, and was my standard deviation, and my sample size is 183. We need to make certain we have a greater than, because that was what we said in our alternative hypothesis, that this was going to be greater than, because we wanted to see if X was greater than Y. And obviously it is greater, it's just whether it's significantly greater or statistically greater, or is it just random chance? So when I come up with this, I get the probability that T, hold on, here we go, probability that T is greater than 1.8459 and that equals a p-value of 0.0328. All right, so this is my p-value. It's greater than 0.01, not significant. But it's less than 0.05, so it's significant at 0.05. So at the 5% significance level, employees at site X have a higher mean salary than those at site Y. Notice it said mean salary. Not everyone has a higher salary, but on average, the employees at site X get paid more than those at site Y. Okay, looking at number 6. Ecologists wanted to estimate the mean biomass. And by the way, this says estimate. That's an important word, all right? They want to estimate the mean. When they use the phrase estimate the mean, probably going to be looking at a confidence interval, because a confidence interval says we don't know where the mean is. We're going to estimate where it is. Whereas a hypothesis test is testing to see if a claimed mean is actually correct. So they want to estimate the mean biomass of a certain forested region. The ecologists divided the region into plots measuring 1 square meter each, and they selected a random sample of 9 plots. The mean biomass of the 9 plots was, and by the way, that's an important word. We have 9 plots, was 4.3 kilograms. So that was our mean. And the standard deviation was 1.5. Assuming all conditions for inference are met, which the following is a 95% confidence interval for the biomean. All right, so here's the deal. First off, that 1.5 standard deviation, that came from the sample. So because this is a sample, this is a t. So our formula for a confidence interval for a t would be x bar plus or minus t star s divided by square root of n. So I'm going to start plugging in. We have 4.3 plus or minus. We'll come back to t star in just a moment. Our mean biomass, our standard deviation is 1.5 divided by the square root of 9. And now I need to go calculate my t star. So second vars, inverse t. And so area 1 minus 0.95 divided by 2, that's our area. And our degrees of freedom for one sample is n minus 1. So in this case, 9 minus 1. So parenthesis 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom was 9 plots minus the 1. And we get a t star of 2.306. So great, that should be my answer. So I start looking for that. Well, they all have 4.3, so that doesn't help me. Then I notice that these last ones have 2.306. Well, that's a good thing, but I still don't see 1.5 divided by the square root of 9. They're just being a little bit tricky math-wise. 4.3 plus or minus 2.306, 1.5. What's the square root of 9? It's just 3. So consequently, my answer for number 6 is E. All right, because I just took the square root of 9. All right, number 7. A new article reported that college students who have part-time jobs work an average of 1.5 hours per week. The staff of the college newspaper thought that the average might be different, so that's a key phrase because that's not equal, from 15 hours a week for the college students. Data were collected on the number of hours worked per week for a random sample of students at the college who have part-time jobs. The data were used to test the hypothesis, where mu is the mean number of hours worked per week for all students at the college with part-time jobs. The results are shown in the table below. Assume all conditions for inference were met. Which of the following represents a 95% confidence interval for the mean? So basically we have X bar plus or minus T star S divided by the square root of N. And basically we know this information is a T star and not a Z because we're working with the sample, all right? So all this information came from the sample and we have a sample mean of 13.755. So that's nice and easy. Plus or minus, we need to calculate our T star. So we're going to go second vars, inverse T. And they wanted to do a 95%. So once again, area 1 minus 0.95 divided by T. And please remember 2. Please remember, if I'm writing it down, you need to as well. Degrees of freedom, in this case, is 25, has been given to us. They've already done the subtraction for us. So please don't make the mistake that I was trying to do just now. They've already given that to us. So degrees of freedom is 25. And I go about calculating and I get 2.0595. 2.0595. But what I'm missing is the S divided by the square root of N. All right, so definitionally, we need to go back to some definitions. This right here, everything after the plus and minus sign, this part over, that is known as the margin of error. What I'm circling right here is the standard error. And they happen to tell us that our standard error is 0.0707. So I just need to come back and multiply this by 0.070, or excuse me, not 0.0707, 0.707. So 0.707. So going to the calculator, multiplying that times 0.707. And I end up getting 1.456. So 13.755 plus or minus 1.456. And that gives us our answer choice for E. All right. Please note, standard error, that's that part of it. Margin of error is anything after the plus or minus. Standard error is the part underneath the standard deviation. All right. Or the part right after T star. When using a one sample T procedure to construct a confidence interval for the mean of a finite population, a condition is that the population size must be at least 10 times the sample. All right. So this is basically N has to be less than or equal to 10% of the population. So N must be less than 10% of the population. The reason for this condition, all right, all year long, Mrs. Lamb and I have both talked to you about the giant pile of M&Ms. And that's about all we can write. Basically, when we take one away, the percentages don't change. So the percent changes slightly. Basically, when I take the one M&M away and eat it, the number of red M&Ms do change. The percentage of red M&Ms do change, but it changes slightly. And we're saying as long as the sample is less than 10%, the degree of dependence among observation is negligible. In other words, it's not really independent, but the sample size was small enough. So basically, it's got to have a small sample size. Our N has to be less than 10%. Number 8 is D. Moving on to number 9. A two-sample t-test of the hypothesis mu1 minus mu2 equals 0. We could have rewritten this, all right? We could have rewritten this and said, and if I write it down, you need to, HO mu1 equals mu2. And our alternative would be mu1 is greater than mu2, all right? Produces a p-value of 0.03. So that's the key part. We're producing a p-value of 0.03. Which of the following must be true? So we're going to confidence intervals. Well, to be a confidence interval, well, first off, all confidence intervals are two-tailed. This is one tail. So write this down. Confidence intervals are two-tailed. Confidence intervals are two-tailed. Going from one tail to two tail, we double our sample size. And double our, excuse me, not our sample size, our p-value. So going from one tail to two tail, we double our p-value. All right, just like on a t-test, we multiply by 2. So in this case, they had an upper tail test. And with that upper tail test, they had 0.03. All right. So they had 0.03. And then but because we went to a two-tail test, we also have a 0.03 down here because all confidence intervals are two tails. So then I go 1 minus 2 times 0.03, and I end up with 0.94. So basically 94% lies within here. So 94% lies within that, 94% lies within the interval. Please remember, as the interval gets wider, as our confidence level goes up, so confidence level up, the interval goes wider. So this means confidence level 95 and 99 are the widest, or 90 is the narrowest, then 95, then 99. This was the rejection zone, all right? This was the rejection zone. So 94% or less would not be rejected. 94% or more would be rejected. So 94% or less, not rejected. All right. And a better way of saying that is, I said that incorrectly, 94% or more. I'm not sure the best way to say this, so I apologize for stumbling, but at this point, anything wider is going to contain 0. So anything wider than 0.94 will contain 0. And I guess that's what we should say. As we get wider, as we will get wider after 94%. So after 94%, we will contain 0, or the interval will contain 0. Less than 94%, it does not. Greater than 94%, it does. So 90 does not, because it's less than 94%. 95% is greater, so it does, and 99% also contains 0. In other words, we could not make a decision. If this went further out, as this went further out, we could not, as we move further out, our confidence level increases, but we got wider and we're going to contain 0. So basically we're saying 0 existed here. So as long as we didn't cross that, we did not contain 0. So 0, I'll say that again, that's important. 0 existed here. If we go further out, our p-value gets smaller, then all of a sudden it contains 0. So anything 94% or less does not contain 0. Anything greater than 94% does. I apologize for the stumbling around. All right, on number 10. A botanist collected 1 leaf at random from each of 10 randomly selected mature maple trees of the sample species, of the same species. The mean and the standard deviation of the surface for the 10 leaves in the sample were computed. Okay, so the mean and standard deviation of the sample. So as soon as we say of the sample, we know we are working with the t distribution, all right? Assume the distribution of surfaces is normal. And by the way, they'd have to be because our sample size is less than 30. What is the appropriate method for constructing a 1 sample confidence interval to estimate the population mean? So the question is, should we be using a T or a Z, and why? Because our choices are all T and Z. Well, we know we have to be using a T because standard deviation of the sample. And what's nice about that is that's actually it is. The T is appropriate because the population standard deviation is not known, and we're using the standard deviation of the sample. So number 10 is pretty short, and that was E. Please make sure you've written down. If I've written it down, you need to make sure you write it down. And any notes to yourself that's going to help you out with this. This will go in your folder. You'll have access to the test questions, and the second video will cover problems 11 through 20. Thank you for watching. I hope you'll join me. I look forward to seeing you in the next one. Bye.